and it can be found on page 37 of the unit handout. So we're going to be determining equations of slant asymptotes. And then although we're not going to be doing examples with this, you're still expected to be able to graph functions completely, including now functions that will have slant asymptotes, whatever they are. So we start off with kind of a statement that's leading up to slant asymptotes. Let's say that you have a function which is actually the sum of two other functions of x. By the way, I'm teaching this to you totally different than how it's taught in your textbook. And I would hazard a guess that if you went to your textbook and you, after this lesson, and you followed through the author's explanation, nothing against the author's explanation, but I think it needs to be boiled down a bit to a high school level. It's quite confusing, I think. So consider a function of the form f of x where f of x is equal to the sum of two different functions. Let's say that as x approaches infinity, g of x approaches 0. So as f of x gets to the very, very far extreme right side of the graph where x is approaching infinity, this thing bottoms out. It gets smaller and smaller and smaller and smaller and smaller. So at large values of x, I don't know that you want to muddy up your notes with this. This is just me explaining. At large values of x, this thing gets smaller. But at large values of x, h of x does not get smaller. So that's what the second part is saying, where it says the limit as x approaches infinity of h of x is not 0. There is no limit to it. It just does whatever it does. If h of x is x squared, then it just continues to be x squared. And when you square x, it gets larger and larger and larger. So what does this mean? It means that at very large values of x, f of x, which is equal to g of x plus h of x, at very large values of x, if this is getting smaller and smaller and smaller, specifically it's approaching 0, then that means at incredibly large values of x, g of x doesn't play any significant role in f of x. So at very large values of x, what happens is this. So as one part of this function gets less and less important, the other part becomes all important. And if h of x is a linear function, then that is what we call a slant asymptote. Let me show this to you numerically before we get to an actual graph. The graph is right in front of you. If we take a look at the function that's in your handout, you have a function in your handout. It is what is in column D of this spreadsheet. It is f of x equals 2x over x squared plus x minus 2, and then plus 1/3 x plus 3. So what is this spreadsheet showing you? It's showing you that when x is 1, the y coordinate on the function is 5.33. When x is 2, the y coordinate is 4.1, etc. So the first column is your x coordinate. The last column is your y coordinate. But what the two middle columns are the pieces of the y coordinate. When you take a look at this function, the first part of it is 2x over 2x squared plus x minus 2. And that's what this column is. This column is the first piece of the entire function. So check out when x is 1. The first piece of the function is 2 point something. The second piece is 3.3 repeating. So when we add these two together, we get the y coordinate. If we take a look at x equals 2, when you put 2 into the first piece, you get 0.5. When you put it into the second piece, you get 4.16. But take a look at column B. As x gets larger and larger and larger, column B gets smaller and smaller. Because the limit, as x approaches infinity, of this thing in column B is 0. Because the degree on the top is less than the degree on the bottom. In fact, if I scroll down here, you can see that it continues to get smaller. I'm going to get rid of that thing. There we go. When you take a look at column B and I scroll down, when I get to very, very large values of x, I don't know where I went to. I went to 297. That first part of the function becomes very insignificant. Now, take a look at what's happening to the second part of the function, which is what's in column C. It goes from 3.3 repeating to 3.6 to 4 to 4.3, and it just keeps increasing. There's a pattern to it, but I really don't care what that pattern is. It keeps increasing. Now I want you to take a look at column C and column D and compare them. When you compare C and D for small values of x, C and D are not even close to being the same. But as x gets larger and column B becomes smaller and smaller and smaller, then column C starts getting very, very close to being the same as column D. And when you take a look at the graph of the function, that's what this graph is showing you. For this function, if you were to graph y equals 1/3 x plus 3, which is not the function, you would get this line. At very large values of x, this part of the actual function gets less and less important, leaving you with the rest of the function, which is 1/3 x plus 3. And that's why the curve is getting closer and closer to that straight line of y equals 1/3 x plus 3. This is a tough concept, so I want to ask this question, and I want everybody to answer honestly. Does that make sense to you? Kind of the responses I would expect. It's not simple. I guess the bottom line is, I really hope this table helps, that when you look at columns C and B, C and B are the two parts of the function that are being added together to get the actual function, which is in D. So when x is 1, we're adding 2 and 3.3 and getting 5.3. I'm going to try this in another way. When x is 1, we're adding 2 for the first piece of the function to 3.3 repeating for the second piece to get 5.3 repeating for the entire value of the function, which is y. Now, is column D, when x is 2, close to column C? Well, close is a relative term. It's 2 away. And the reason it's 2 away is because column B is 2. When you take a look at x equals 2, is column C closer to column D now? And the answer is yes, it's closer. And the reason it's closer is because this number, if I can get it, is because this number that I've highlighted has gotten smaller. And when that number gets really, really small, the difference between C and D is not that important. So think about what I've just said here. I just said that at large values of x, the difference between C and D is not as important. Okay, well, wait a minute. The difference between columns C and D is not that important. Well, that means that at large values of x, this must not be that important. The function is just turning into, slowly turning into, something that looks more and more and more like 1/3 of x plus 3. Let's get into the examples now and see if this helps clear the cloudiness from this. So what is the equation of the slant asymptote of this function? Let's take a look at it. First of all, we have two pieces to this function. We have 2 over x squared minus 3, and then we have minus 4x plus 2. Well, as x approaches infinity, this approaches 0. And I'm really using a shortcut here. I don't want to have to find the limit. I'm just using the shortcut that says when the degree on the top is smaller than the degree on the bottom, the limit as x approaches infinity is equal to 0. So what does this mean? It means as x approaches infinity, y approaches 0 plus negative 4x plus 2. We've just established that this is approaching 0 at infinity, so y will be approaching that 0 plus the remaining piece of it, which means as x approaches infinity, y approaches negative 4x plus 2. So that must be the equation of the slant asymptote. What I've done on the board here is a totally different approach. I'm not playing around with numbers right now. I'm playing around with the concept of a limit. I'm going to ask the same question again, and I want everybody to answer. Does that explanation make sense or help out a little bit? Okay, so the fact that the responses were coming a lot quicker and they're all saying yes with the odd exception makes me feel good about that. And that's why sometimes in math you need to hear things in a couple of different ways. And it's not that one way is better, you just need more explanations. So let me show you the graph now. That's the answer to the question. Here's the graph. Hopefully, there it is. So what have I got here? I want to take a look at this first. Okay, there's the graph of the function. It's a pretty wacky function, and you could certainly use all of the tools at your disposal to find out concavity, points of inflection, increasing, decreasing. You could do all of that. I'm going to abbreviate this graph so it's a little easier to look at. I'm going to look at it in 3 pieces. And that's what it looks like. Now, if I graph the equation of the slant asymptote was negative 4x plus 2, that's what I've just turned on. It doesn't matter, everybody. Oh, and by the way, you do have vertical asymptotes as well. But it doesn't matter what the graph is doing, say, here, Or here, what matters is as x gets large. And as x gets large, you can see that this curve, which is the function, is getting closer and closer and closer and closer to the line 4x, negative 4x plus 2. In fact, I'm going to go back to my graph. And I think maybe I should have shown you and talked about the graph to begin with. I'm going to go back to my graph and turn these off and go to the whole graph. And I am going to zoom out. And now if you take a look at the far left piece of the graph, it's incredibly close to that dotted line. In fact, I don't know what it's appearing as it makes its way through all of the magic of the internet to your device, but even where I'm standing, I have a hard time seeing any space between the two. If I zoom out even more, you see that basically at very, very large values of x, that brown function is actually getting really, really close to that slant asymptote. It's called a slant asymptote because it's at an angle. If we were to take a look at, this graph, it's the same kind of thing. On a scale of 1 to 10, how do you rank your understanding of it now? Okay, I would say that's pretty good because the class average in this class is somewhere between 80 and 90%, and that's basically what you're saying. Now we get a little bit of a twist because you can tell basically that the slant asymptote is this negative 4x plus 2 by looking at the equation. I'm going to erase all this. You can tell by looking at the equation because there it is. It's not always going to be that simple. So let's take a look at examples 2 and 3 now. By the way, I don't believe this is in your notes, but anytime you have a rational function where the degree on the top is more than the degree on the bottom, you're going to have a slant asymptote. And essentially, if the degree on the top is 1 more, that slant asymptote will be linear. And if it's linear, that's what we call it, a slant asymptote. So let's take a look at this next one. Find the equation of the slant asymptote for that function. Okay, wait a minute. What we want to do, everybody, is rewrite that function into one function. I want to make sure that I'm using the same letters I used before. One function, g of x, that will approach 0 at large values of x, plus another function which will be the linear asymptote. When you look at example 1, it was already given that way to you. What we have to do is take this function in example 2 and turn it into something that looks like that. So this is going to approach 0 as x approaches infinity. The other part, h of x, is not going to approach 0, but it's going to be a linear expression. How do we do this? Well, we're going to do division. We're going to divide 1 plus x minus x squared by x minus 1. And we can do that with synthetic division. Just want to make sure I wrote that down correctly. I did. I'm writing it this way because in synthetic division, you put the coefficients of the numerator all the way from the highest degree to degree 0. So I had to rearrange the order of those items and put the x squared first, then the x, then the 1. Here you put the 0 of the polynomial that you're dividing by. This is the 0 of 1 goes there. We move this down. You multiply the 0 by whatever's below the line to get negative 1 in this case. You add them to get 0. You multiply 1 by 0 to get 0. You add them to get 1. Okay, what does this mean? There is a reason we do this in Math 30-1 that goes beyond working with polynomial functions. You need to know how to divide polynomials. What this means is that negative x squared plus x plus 1 over x minus 1 is equal to, this is the quotient, and remember that if this was degree 2, this is degree 1. Whenever you do synthetic division, the degree drops by 1 because you're dividing by x to the 1. So the quotient is actually negative x and then plus nothing, and this is the remainder. But this division of negative x squared plus x plus 1 over x minus 1 is not equal to negative x plus the remainder. It's plus the remainder over what you were dividing by. I want to go to my go-to example for division to illustrate this. If I say to you, what is 26 divided by 3? With a little bit of thought, you should understand that 3 goes into 26 8 times. I hope. But you've got some left over. So if I had 26 Smarties and I was going to give 3 people all of the Smarties, each person would get 8, but then I'd have 2 Smarties left over. Because 8 times 3 is only 24, and I had 26. So the rule is we add the remainder over the quotient, or not the quotient, the divisor. You can feel free right now to use your calculator and calculate 26 divided by 3. You will get 8.6 repeating. You can use your calculator to take 8 plus 2/3. You will get 8.6 repeating. So what have we discovered? We've discovered that this function, this is y, can be written instead this way. So in this example, we can write f of x as 1 over x minus 1 plus negative x. Notice on the page that I just came from, I said that y was equal to negative x plus 1 over x minus 1. This, as x approaches infinity, this thing approaches 0. So that's the part that we're calling g of x. It's approaching 0. The other part is not approaching 0. It's just going to get, well, larger is the wrong word because it's negative, but it's going to get bigger and bigger and bigger in value in a negative direction. And what this means is, since this, I'm going to give one more kick at the cat, horrible expression, but I'm going to do it again. As x approaches infinity, this thing will approach 0, which means f of x will approach 0 plus negative x, which means f of x is approaching negative x. The slant asymptote is that. Let's take a look at the graph. So here's what the graph looks like. Again, I'm going to graph it instead in two pieces so that you can see the asymptotic nature. This function does have an asymptote that's a vertical asymptote, and if I graph now y equals negative x, that's what that line is. So it's not a horizontal asymptote. The graph isn't approaching the x-axis, for example. If I zoom out, you can see the same kind of thing happens that we talked about before. Questions with example 2? All right, so with example 1, we didn't have to do any division because the thing was already written in a nice form where we could just look at the slant asymptote. In example 2, we had to do division, and we used synthetic division for this one. Now, example 3. Well, we can't use synthetic division here. And the reason you can't use synthetic division is the denominator is not a linear factor. But we're still going to divide. We're going to have to do long division. And in my Math 30 class, when we do long division, at the time, I show you long division and then say, but unless you're going to move on and take calculus, don't worry about it. You can always use synthetic division. Well, now it's time to buckle down and use long division. You can't use synthetic division here. So we are going to have to divide 2x cubed minus 3x squared plus x minus 3. We have to divide that by x squared plus 1. So we're not just putting the coefficients, you're writing the entire polynomial including the x's. It's not difficult, it's just something you don't do very often, so it takes some practice. All right, your first step. Well, with long division, you divide, you multiply, you subtract, you repeat. This is what you do with long division. So I will give you a minute to write that down if you like. However, when you divide, you only divide the highest degree terms. In other words, in the division step of this process, we're only dividing x squared into 2x cubed. We're only looking there. So when I divide x squared into 2x cubed, I'm just going to write down what I'm thinking and then erase it. What I'm saying is, what is 2x cubed over x squared? That's what I'm thinking. That's what's going on in my head. And I see that I get 2x. And the rule is that after you do that division, you have to put the result of the division in the column of the same degree. So when you divide cubed by squared, you get linear. We have to put it in the column that has linear terms. So we've done, I guess, the first step. We've divided. Now we're going to multiply. What do we do here? You take whatever you put up top. Give me a second. You take whatever you put up top and you multiply it by what you were dividing in. And this time, when you multiply, you have to multiply by the whole thing, not just the x squared. So when you divide, you only divide by the highest degree term, but when you multiply by them both. So what will that do? That will give us 2x times x squared is 2x cubed, which you have to get. If you don't get the same thing that you were dividing into, then you did it wrong. And then 2x times 1 is 2x, so I have to write that over here with the x's. And now what we have done is the second step. We've multiplied. Now what you need to do is the third step, which is to subtract. So be very careful when you do this. You're subtracting the entire thing. So 2x cubed minus 2x cubed is nothing. You don't need to write anything here, but I have seen some people write 0x cubed. You don't need to do that. I guess we do have 0x squared here. We cannot leave this negative 3x squared out of the game. It's a player. Negative 3x squared minus 0x squared is negative 3x squared. And then x minus 2x is negative x. So just to make sure that you are with me here, (2x cubed minus 2x cubed is nothing. Negative 3x squared minus nothing is still negative 3x squared. And x minus 2x gives you negative x. And what we have done now is step 3. And we're going to repeat. Okay, well, wait a minute. How do we know if we can repeat? Well, go back to the beginning and look at divide. Can you divide this into this? And when I say can you do it, we never want negative exponents. The answer is sure. What goes on in my head here is I'm taking 3x squared, well, negative 3x squared, and I'm dividing it by x squared. And I'm seeing that it's possible to do that, and I get negative 3. So what I have done now, I'm not going to put a check mark beside repeat. I'm just going to go back up to the top. What I have done now is I've done division in my second round of steps. Remember, when you divide, you only worry about the highest degree terms, but when you multiply, when we go to the next step, when I go to the next step and you multiply what you got by the entire thing you were dividing by. So that's negative 3 times x squared gives you negative 3x squared. Negative 3 times 1 is negative 3. You've got to put it in the right column. And now we have multiplied. By the way, if you just want an answer, that thing at the top, 2x minus 3, is the asymptote. The asymptote will always be the quotient, and I'll come back to that idea in a second. We've now got to subtract. So do the same kind of thing just so you can follow it along. If I take 3x squared minus, well, negative 3x squared minus negative 3x squared is nothing. I have negative x minus, if you like, you can put 0x here, but you're going to get negative x. And then I have, just a second here. Well, that's interesting. You do have to bring down, I'm going to change this example for next time. I never intended this to be. You do have to bring down this next item. You have to, okay? So I also need to take negative 3 minus negative 3, which is 0. So what we're going to end up with is negative x, and then we'll get 0 here. So the remainder is actually negative x. Um, if I had to redo this lesson, and I will, I do not want those constants to cancel in the end, but it doesn't affect the question. What does this mean? It means that this original function is equal to the quotient, which is 2x minus 3, so the original function is equal to the quotient, which is 2x minus 3, plus the remainder, which is negative x over the divisor. So this is the function. It's written in an alternate form. If you were to graph the original function or look at a table of values of the original function, and you were to graph this thing, you would get the same result. So I'm going to rewrite this as y equals negative x over x squared plus 1 plus 2x minus 3. As x approaches infinity, this thing will approach 0. I'm going to stop there. How many of you could explain to me why this thing is approaching 0 as x approaches infinity? How do you know it does? Exactly. That's the exact reason. We could figure out the limit as x approaches infinity of this, but if the degree on the bottom is larger than the degree on the top, that rule from Math 30-1 is very useful. That means it will approach 0. So as x approaches infinity, that approaches 0. That means as x approaches infinity, y will approach 0 plus 2x minus 3, which means y equals 2x minus 3 is the slant asymptote. Let's take a peek at the graph. This is the graph. It looks like somebody had too many drinks and then tried to draw a straight line. There's a kind of a stagger to it. But it is actually approaching. This is the line y equals 2x minus 3. It is actually approaching that. If I take a look at a zoomed out view, this is what it looks like, and you can definitely see that it's starting to get closer and closer and closer to that dotted line, which is y equals 2x minus 3. Even further out, you can see it's getting even closer, and far out, it gets really close. If you start to zoom out more and more and more, I guess I won't bother. If you zoomed out more and more and more, you'd be hard pressed to even know that there's that wobble in the middle, because the whole thing would look like the line. So any questions with example 3? It's a weird idea. I want to, well, first of all, this is elective material. This is not going to be on your exam, okay? But you could very well encounter it next year. I want to point out to you that asymptotes don't have to be lines. They don't have to be linear. Take a look at this function, y equals x cubed plus 1. If I were to do synthetic division, could I do synthetic division? I guess I couldn't. If I were to do long division here, since the degree on the top is 3 and the degree on the bottom is 1, my quotient would be x squared. Now just look at this function. I'm telling you that these two things are the same, okay? So as x approaches infinity, y will approach x squared. As x approaches infinity, y is going to approach x squared because 1 over x will get smaller and smaller and smaller. So let's take a look at the graph. That's what the graph looks like. This is x cubed plus 1 over x. There is a vertical asymptote. This is what the graph actually looks like. It continues, but I'm going to graph y equals x squared. Look at that. There's y equals x squared. The graph, x cubed plus 1 over x, is approaching x squared. It doesn't look like x squared here. It only starts to look like x squared when x approaches positive or negative infinity. Give you another example here. Take a look at this one. Now, I actually have these in the opposite order, but as x approaches infinity, this will approach 0 because the degree on the top is smaller than the degree on the bottom, which means as x approaches infinity, y will approach sine of x. What does that mean? Okay, well, let's take a look at the graph. That's what the graph of sine of x plus 2x over 3x cubed, I can't read what it says, I don't remember. That's what the function looks like. Here is what sine of x looks like. And again, you can see in the middle region, the graph doesn't behave exactly like sine of x, but if you extend the graph and zoom out, the two graphs become virtually identical. They get closer and closer to each other, which is kind of an interesting thing. Anyway, a little bit of practice here with this. You can use some of this time to practice on slant asymptotes. You can use some of the time to polish up your assignment if you haven't submitted it. You can use some of the time to work on any other math. There was a long time to go without a break, so take a break, of course, if you need to. Please note that I do not want you doing number 3 if you're going to work on these slant asymptotes. Number 3 relies on you understanding your author's explanation, and I don't think it's worth going there. Too fast, too slow, or just right? Okay, I hope you got over your initial confusion over this and you get it now. I'm going to mute my mic and just get my video set up for importing to YouTube. So if you need questions answered, please give me a shout.